Hello. In this video, I'd like to demonstrate how to use Excel and your graphing calculators to do correlation and linear regression analysis. And maybe if you're lucky, my little doggy Freddy will chime in because he's already started barking at me now that I'm recording this video. So, let's look at this problem number 15 from sections 10.2 and 10.3. It reads, Campus Crime. Selected below are numbers of enrolled students in thousands and numbers of burglaries for randomly selected large colleges in a recent year, based on data from the New York Times. Is there sufficient evidence to conclude that there is a linear correlation between enrollment and burglaries? Do the results change if the actual enrollments are listed as 32,000, 31,000, 53,000, and so on? So here are 10 pieces of paired data where we have the enrollment for a college and the corresponding number of burglaries in that area. And what we're interested in determining is if there is a linear correlation between enrollment and burglaries. Now, in Excel, I've already taken the liberty of inputting the data. One of the things that we use just at a glance to determine if there is possibly a linear correlation is to look at the scatter plot for the data. So I'm going to highlight my two columns here, not including the labels of enrollment and burglaries. I'm going to click on the Insert tab and then click on Scatter to create a scatter plot. Now, I just need a basic scatter plot, so I'm just going to use the first one. And there I go. I get this graph of the points of enrollments and burglaries. There's Freddy, you can hear him now. And it does appear there is some relationship because you do see a trend here. There is an outlier, it appears, but overall, we do see a trend. Now, is a linear correlation the most appropriate way to model this trend using a linear regression? And that's what we're going to determine because it may be a line, but it might be some other type of curve, like maybe a power curve or maybe a logarithmic curve. But for now, we're interested to know is there a linear regression most appropriate to model this data with? So we need the linear correlation coefficient. Now, using your graphing calculators, I've also taken the liberty of inputting the data into lists, list 1 and list 2. And to graph this data, I go to stat plot, which is actually the secondary option above y is equal. Shut up, Fred! And so I hit second stat plot. Now, all my plots are off, so I'm going to select the first one. I'm going to turn it on by selecting the on option and hitting enter. And by default, the scatter plot is the first one chosen. So I'm going to leave that selected. The X list, I'm going to leave as list 1. The Y list is list 2. If you're using two different lists, then input them appropriately in X or Y. And then for the mark, I'm going to leave as this open dot. You could choose your dots to be this, plus sign, but don't select just the individual dot. Those graphs are so tough to see. So I'm going to use the open dot. And when I'm ready to graph this, I'm going to click Zoom now, which is also a button below the screen. And I have to scroll down just a little bit to find Zoom Stat. What's nice about Zoom Stat is it'll automatically adjust your window settings appropriate for the graph that you're plotting. So I click on that, and I get this nice scatter plot, which looks similar, but the scale along maybe the vertical axis is a little bit different. Or maybe it's the horizontal axis. However, you do see an overall trend here that would lead you to believe there is some type of correlation. We're just interested to know, is it a linear correlation? So, what we're going to be interested in knowing is if there is a population linear regression that exists between enrollment and burglaries. Now, if the population linear correlation is equal to 0, that means there is no linear correlation. But if there is something that's significantly different than 0, positive or negative, then there is a linear correlation, and that's what we're going to want to test. Now, in order to perform that test, we have to calculate a test statistic using the sample correlation coefficient. So we do need to find lowercase r, the correlation coefficient. And in Excel and even in your graphing calculators, these are really quick. And not only are they really quick, but often at times the actual equation for the linear regression is not far behind. Now let's go back to Excel. We already have the scatter plot, and if I want to find now r squared and r, meaning the correlation coefficient and the correlation coefficient squared, I simply click on one of these dots, and it should select them all. Notice how all of the dots are selected. Now I'm going to right-click on my selection, and I'm going to add a trend line. By selecting that, it opens up a dialog, and it's going to ask you, all right, first of all, what type of regression are you interested in? Because there are many more types of correlations and regressions. In Chapter 11, we primarily talk about linear, but look at all the other common types here. Exponential, logarithmic, polynomial, power, a moving average. We even have some that aren't included here, like trigonometric ones. But we're going to keep linear selected. And then down at the very bottom, we want to make sure that display equation on the chart is selected and display r squared value on the chart. So once those options are selected, I'm going to click close. And now, look, on your graph, it includes a couple pieces of information. Y is equal to 3.467x minus 36.767, and r squared is equal to 0.3151. Well, remember, what we're interested in finding is r. Well, and r squared, I suppose. That's part of the equation. But in this case, they just gave us r. Well, if they give you r squared, then finding r is not that terribly difficult. You can just break out your calculator and find the square root of that value. So if r squared is 0.3151, 3151, then we just need to take the square root of that to find r. So in this case, if I take the square root of 0.3151, I get my value of r, approximately 0.5613. Now, on the graphing calculators, if you wanted to find r and r squared, you need to do one thing before you proceed. Down at the bottom, there should be a catalog function. It's the secondary function of perhaps 0. It might be somewhere else on your calculator if you have a newer calculator or maybe an older calculator, but a catalog. That's the secondary function of 0. Now, once you're in the catalog, you'll need to scroll down until you get to the D's, which isn't very far to go. But once you get down there, you'll want to find diagnostic on. Diagnostic on, when you select it, will appear on your calculator, and then just hit enter and it'll say done. You need this option to be on in order to get R. Once you've turned diagnostics on, and once you've done that, you'll never have to do it again unless you reset your memory or you change your batteries. But now that it's on for good. Now, let's go back to Stat and then to the Calc submenu. And what we're going to want to do to find R is option Linear Regression, LINREG. And then in parentheses it says AX plus B. Actually, what's interesting is if you look down a little bit farther, there's another linear regression that says A plus BX. They're the same function. The only difference is option 4 is going to give you the equation of the linear regression in the form AX plus B, meaning the slope times X plus the intercept. And the other one is going to give you the linear regression of the form intercept plus slope times X. They're really the same thing. They give you the same equation for the line. It looks a little different, but it's not. However, both functions will give you the same R and R squared. So I'm going to select linear regression, the first one. And then if you are using any other lists besides L1 and L2, you'll have to type them in. So like in this case, I could type in list 1, comma, and then list 2. Or if you're using any other list, you have to pair them like that, separate them by commas. Now, if you just have list 1 and list 2, you don't have to specify them. But here we go. After you're done specifying the two lists, we hit enter. Ooh, look, and Freddy's getting ready for it. Shut up, Freddy. And you can see here I have r squared is equal to 0.315053973, which is very close to what Excel gave us, but Excel rounded it. And you can see we also get something very close to what we got when we took the square root, 0.5612966,889. However, if you round it to the nearest, tenths, hundredths, thousandths, 10,000ths, it's 0.5613. So we do get the same r and even r squared. And notice we get the same equation for the linear regression. Y is equal to a 3.467x plus b, a negative 36.7669, on and on and on. But now that we have our r, we can calculate now our test statistic for our hypothesis test of whether or not the population correlation coefficient is equal to 0 or not. So just to review, in Excel, we're going to insert a scatter plot, we're going to add the trend line, and then make sure that display equation on the chart and display r squared value on the chart are both selected. You can see, as another review, now we're given r squared, but we can find r just by taking the square root of the r squared to get our correlation coefficient of 0.5613. And then if we need it, we also have the equation of the linear regression, the predicted value. In this case, since we're talking about burglaries and enrollments, and we're using enrollments as x and burglaries for y, we could say the predicted number of burglaries will equal 3.467 times the size of the enrollment minus 36.767. In the graphing calculator, make sure your diagnostics are on, and then select Stat, Calc, and then Linear Regression. And then if you need to, also include list 1, list 2, or whatever two lists you're using. And you can see, like before, we get not only r squared and r, but we also get the equation for the line. The same results that we got in Excel, including the same linear regression. So, taking our value of r, 0.5613, and our sample size of 10 pairs of data, we get a sample statistic of 1.918. Now that we have the test statistic, we can compare that to potential critical values, or we can calculate the p-value using 8 degrees of freedom, n minus 2, in the direction now of this test statistic. And using Excel, for example, since we're dealing with a two-tailed test, then what we're interested in finding is the two-tailed area in the direction of the tails, the alternative tails. In Excel, I can find that by the following function. So here, I'm just going to type in p-value, just to label it. And in the cell next to it, I'm going to type it in. I want a t-distribution, and specifically, I want the area for two tails relative to my test statistic. So I'm going to select this function here, t.distribution.toTails. And notice it takes arguments of my test statistic and the number of degrees freedom. So if I use now my test statistic of 1.918 and 8 degrees of freedom, yeah, you can see what we get. 1.918, 8 degrees of freedom. I just wanted to check and make sure that was the right numbers I'm typing in. And then enter. And you can see that I get a p-value of just a little bit more than 9%. Now, that's important because if my p-value is a little more than 9%, that's certainly greater than the desired level of significance from the problem. And when the p-value is greater than the level of significance, that tells you the test statistic has to be well within the non-critical region, which tells us not to reject the null hypothesis. Well, if we're not rejecting the null hypothesis, then remember the null hypothesis says there is no linear correlation, and we're not rejecting that. Therefore, we can't support the claim that there is a linear correlation. So even though we do see a relationship in our graph, it's probably not the best relationship. Therefore, we won't use a linear regression. I mean, but one of the nice things about all this technology is that not only, do we get R, but if there were a linear regression, we would have it. And that concludes this video.